Hello, good evening and welcome back to the online interactive lecture series of the INO project that you have been part of for many weeks now. And today we have Professor Tarun Souradeep from IISER Pune going to talk on LIGO-India, ushering in gravitational wave astronomy. Um, for Tarun, I think for many people on the call is well known, but just take a minute to introduce him. Tarun graduated as an engineer from IIT Kanpur, and interestingly, before he decided to kind of pursue a PhD in gravitation and cosmology, he actually had a short stint in automobile design. He then has built and led a cosmology subgroup on cosmic microwave background studies. Souradeep led the sole Indian group within the international team of the Planck CMB space mission of the European Space Agency. And his contribution to science has received many international recognition. He has been elected fellow uh, of the International Society in General Gravity and Relativity and Gravitation in 2013. And he's a co-recipient of the Special Breakthrough Prize in Fundamental Physics in 2016 and Gruber Cosmology Prize in 2016 for the recent then discovery of gravitational waves at the time. He's also recipient of a number of awards in India, including Swarna Jayanti Fellowship, National Academy of Sciences India, Nasi Scopus Award, B.M. Birla Prize, Vikram Sarabhai Research Award, fellow. He's a fellow of the Indian Academy of Sciences and the National Academy of Sciences India. And he serves as the spokesperson for the LIGO-India Mega Science Project for the construction and operation of gravitational wave observatory on Indian soil. So he's of course going to talk about all these efforts, both from the point of view of science that the LIGO has produced, but also the efforts that are currently on to have one such facility and station in India in our own state, Maharashtra. So with these few words, now I invite Tarun for his lecture.
Thank you, Satya. It's a pleasure for me to present the status of LIGO India and the excitement that it promises at a forum of our elder sister mega science project, the Indian National Neutron Observatory. And I must say that it's always been a guiding light for us to see how INO moved and various respects. We have been, we have learned a lot of things from how the INO has progressed thus far. So it's a pleasure, and I'm really glad to also see many stalwarts of the Indian neutrino field out here. And then, I hope that I'll be talking to more students than such renowned people. But let's see. And so I will give you, present to you the LIGO India project and its main, reason for being, and that is to usher in gravitational wave astronomy. So even when we first proposed heaven, getting to be part of the discovery with a facility in India, and we were targeting the fact that we will be enabling gravitational wave astronomy, and that is very clearly mentioned in our thing. I'm at IISER Pune, and behind me you see is a rendering of how LIGO India will look. This is from actual architectural drawings, and I'll show you the status soon. So the story begins.
Tarun, can you speak a little louder, please?
Sure.
Yeah, please.
Can you hear me now?
Yeah, better.
Okay, good. So the story begins about a century back with Einstein's proposing his general theory of relativity as the theory of gravitation. And soon after that, in a year from then, he predicted the gravitational waves as a solution to his equations. And this is the from cutouts, courtesy Revise, of the original paper of Einstein 1916, where he talks about gravitational waves. And he actually points out that the amplitude, he computes the amplitude and says that in any case, one can think of A will have a practically vanishing value. So he never thought this would be something of which frontier in physics and astronomy will be emerging at the time that he predicted it, because it is true that gravitational waves are extremely weak signals, and I will tell you how weak they are in slides to come. So let me place the idea of gravitational waves. So you know that general relativity is an extremely elegant as well as very successful theory of gravitation. And how it works can be captured in these two lines due to Wheeler, which says matter tells space-time how to curve and space-time tells matter how to move. And this interplay between matter and space-time geometry actually governs the laws of gravitation. So when we see the Earth moving around the sun in an elliptical orbit, it's actually the sun's gravitational field which has warped space-time so much that a straight line on which Earth is moving in that space happens to be an ellipse. Okay, and this is the feature of curved spaces. So like the surface of the sphere, the straight lines on that are great circles, and this is essentially how gravity, just like two longitudes converge at the pole, objects seem to attract each other because of the curvature of this space-time. Question is that is very well established and very well measured in the largely static cases, very slowly moving masses. But if the mass is moving very rapidly and also the masses are big enough, then there is a significant effect, and that is, you essentially perturb space-time such that waves are generated which propagate out at the speed of light. And so they're very similar to electromagnetic waves as being transverse and have two states of polarization. The states of polarization are slightly different from electromagnetism, being a spin to field gravitational waves. Uh, two polarization states are a bit different, but I will get to that a bit later. But what I wanted to emphasize to you how important this discovery was. Gravitational waves was the first non-trivial, prediction of general relativity. Non-trivial in the very sense I'll explain. Most other effects in general relativity, you can try to reproduce by modifying the Newtonian potential of gravity. But Newtonian potential of gravitation cannot accommodate, Newton's gravitational theory cannot accommodate gravitational waves. Okay, so this is a qualitatively unique feature of general relativity versus Newton's gravity. And that has now been directly verified in 2015. Okay, so this is basically an animation most to guide the students. Let me see if I can get it going. Yeah. So this is what is happening. Essentially, if there are two very dense objects, say two neutron stars, orbiting each other, then they lose energy through gravitational waves which are sent out, and they will slowly merge into each other because of this loss of gravitation, energy through gravitational waves that I am emanating from it. It's very similar to how a dipole antenna radiates electromagnetic wave. Here, you know, the lowest multipole is actually a quadrupolar one, but that's more for experts, not for everyone. So what happened? When did we get to know about gravitational waves? Of course, theoretically, yes, but observationally on our own, man-made apparatus, on 14th September 2015, these gravitational waves were like messengers coming at light speed and brought to us a news of some event that happened long, long time ago and in a galaxy far, far away. People who are Star Wars fans would realize uh, where I have borrowed the style of lettering. And it's actually a billion light years away. And there's some galaxy in a distant universe where the Milky Way of that galaxy, or the galaxy, if you were in a planet in that galaxy looking out, would look very much like our Milky Way, except that these two black holes, if you peer very closely, would pockmark space, the distribution of stars, because they would lens the light around them, and they will sort of shield light coming from behind them, right? So they lens it around them rather than this. So this picture is very beautiful because now these two black holes cannot be sitting next to each other. They have to fall into each other, or and the way they orbit each other is, like any of the orbits that initially very Keplerian. But you can see as these massive objects move around, they churn space-time so much that it is reflected in the images of the stars behind. So the stars behind the black holes, and you can see their motions, reflect that there is some churning of space-time happening there, because the gravitational lensing effect is wildly varying. Okay, so I'll just and continuously. Yeah. So you can see that not only there's action around it, there's also kind of a lot of action between the two things till the black holes touch each other and forms a single black hole. Okay, and when it does form a single black hole, the black hole settles down to a regular shape, and all its deformities it sheds in some nice kind of a ringing tone, uh, which is seen afterwards. So essentially, this is the story that happened in the galaxy far, far away, uh, two black holes merging into one black hole. And the signal we saw are the traces you see below. So they were seen at two detectors in the US, placed 3,000 kilometers apart. And they saw the identical trace 7 milliseconds apart. And it was a telltale signature of a black hole merger. And in one go, there was a hat trick of discoveries made. So this was the first direct detection of gravitational waves. This is the direct detection of a black hole, because the quiver at the end, when the final black hole settles down, is really unique to black holes. Very difficult to imagine something else doing it. And it was also, for astrophysicists, the first detection of a black hole binary systems. So we know that black hole binary systems exist. And there were more surprises. The black holes had huge masses, much larger than anything that X-ray astronomers had imagined till this event. I wanted to emphasize that India has been in this field right from the beginning. Even very early on, Professor Vishweshwara, as a graduate student or maybe postdoc time in Maryland, wrote this paper in Nature, where he predicted this final quiver of the black hole, which is called the ring down signal now. And in the early 90s, Dhurandhar and Satyaprakash did some very important work and laid the foundations of data analysis for gravitational waves, how to get the signals out of the data that you get. It's a very noisy data, and you have to pull this out, and they developed the foundations for the data analysis. And Bala Iyer and collaborators in France laid the foundations of source modeling. What kind of signals are expected from different mergers, of different masses or different, So these were very delicate calculations done, and these were the first things in the field in the early 90s. Uh, and I should also, I'm very proud to mention that all three of these gentlemen, Satya was postdoc with Surinder then. Now he's a very top level player in the field at Penn State. But Satya, Sanjeev Dhurandhar, and Bala Iyer in the last few years, have all been elected to the fellowship of the American Physical Society. Sanjeev joined this year, and Bala a few years earlier, and Satya, I think, last year. And that sort of really shows that Indian science is recognized at a global stage. Now, let me go and tell you what is happening with this black hole mergers. Okay, so here is something called numerical relativity. These equations of Einstein are extremely nonlinear, and beyond a point, analytic techniques fail, and you have to actually just simulate the whole thing on a computer. It's an extremely important field, and it's very well developed now. So what you see here is a black hole right there. And what is shown in the color panel is the gravitational potential. So you can see that the gravitational potential is very deep, the red part where the black hole is, and falls off as 1 over r as you would expect. There's another black hole somewhere in this corner on your left, right? And as I start the movie, you will see these black holes orbiting, and the dynamics of space-time marked by the changing colors of the gravitational potential, and more importantly by these arrows, which are essentially space-time momentum fluxes. Okay, this is something that doesn't exist in Newtonian gravity. Okay, Newtonian gravity doesn't have the space for it, in the sense that it's not rich enough to include that. Whereas in general relativity, you can think of these vectors as space-time fluxes. For again, since there are quite a few experts in the audience, the color code is the lapse function, and the arrows are the shift functions in a 3+1 decomposition. And what you see at the bottom panel is the signal that a detector, ideal signal that a detector would see. Okay, and you can see that starts off as the two black holes are far away. Pretty much, it would be, now it's so far away that it's not in the LIGO band. At some point, when it comes close enough, it will, show up on the trace. And you'll see initially, it would be largely sinusoidal. It would look like a sine curve. You can see it's almost sinusoidal, but the frequency is ever increasing, and the amplitude is also increasing as a power law. And you can see as the black holes come closer, the frequency will really shoot up, as so will the amplitude. So in the detector, it sweeps the detector from low frequency to high frequencies as the black holes merge. And you can see as the black holes merge, the Newtonian potential has created a common envelope. And this is the time when their ISCOs merge, and ISCO is the smallest radius before which the black hole just plunges in. And you can see now the quasi-normal modes leaving the system, okay, with the black hole settles. And these gravitational waves then travel out freely, and they travel for billions of years and come to us, hoping that we have detectors sensitive enough to detect them. So what we detected in the first event itself was something where, I would like to call it physics of the extreme. Everyone talks about, extreme cases of physics in various settings. Let me tell you how extreme this is. Here is a 30 solar mass black hole. Physically, it would be the size of a city like Pune. And maybe the 40 solar mass black hole will be the size of Mumbai. Okay, that's the kind of radius, diameters these will have. And the total mass was about 70 suns, which would be like a district size. So these are terrestrial sized objects, but they pack 30 times the mass of the sun, 40 times the mass of the sun, and 70 times the mass of the sun. And I should remind you, the mass of the sun is 10 to the 30 kilograms, I think. Okay, something of that order. Okay, and so this is enormously dense objects. The important thing is uh, that when they are merging, they actually are moving at crazily high velocities. So the velocity at the time of the merger, exceeds half the speed of light. So these are pretty much relativistic systems. So we have heard of protons, relativistic protons clashing into each other at LHC. These are black holes of 30 to 40 solar masses, which are crashing into each other. Okay, and at the speed of light. I mean, at relatively comparable speed of light. So the physics you get is extreme kind of physics. Okay, and it's extremity of the also the theory of relativity, because you are testing how good Einstein's equations are at such energies. So what kind of energies are involved? So I often used to say that the universe is buzzing with gravitational waves and we haven't seen them, because this event, for example, the energy output within 2.2 seconds was equivalent to 3 solar masses converting into from matter to radiation, gravitational wave radiation, using E equal to mc square law. Imagine what a neutron bomb does, right? It only converts minuscule amount of neutron, protons and neutrons into each other in those fissions, and the mass loss is very tiny, and that is destructive enough. This is 3 solar masses of matter. So 3 into 10 to the 6 times 10 to the 30 kilograms of mass being converted into energy. Okay, if you multiply by c square. So that is like 10 to the 56 ergs per second, or 10 to the 49 watts. That is the power output of this event. So this is more energetic than any electromagnetic phenomena ever observed. And the luminosity is equivalent to the electromagnetic emission of all stars in the universe. So this is a kind of physics that is opened when we start looking at gravitational waves. There's another kind of physics that opens up, and that happened a couple of years later on 17th August 2017. We also, we had detected many more sources by then, but this was the first collision of neutron stars. Neutron stars different from black holes in that black holes are almost geometrical objects. You don't know what the structure is inside. It's clothed in some space-time structure, which does not allow light to even get out, no information to get out. Neutron stars are solid objects made up of neutrons. So it's like a huge nuclei, weight nuclei. So something like a 1.45 solar masses of just nuclear matter, tightly bound by gravitation. And they crash into each other in the same way that I described earlier. So it produced gravitational waves which were detected by LIGO Hanford, LIGO Livingston, and sort of by Virgo also. Okay, not so strongly. So gravitational waves were detected, but at the same time, a satellite picked up this signal in gamma rays, right? And the gamma rays satellite showed an excess just few milliseconds after this, 1.7 milliseconds after this event was detected in gravitational waves. And later, because what happens is neutron stars collide, it also produces a lot of light, because these are nuclear matter which hit each other, get into very dense configurations where a lot of nuclei form, and they also shine and give out signals of our process nucleosynthesis. I'll talk about that. And these were seen in follow-up observations in optical, X-ray, optical, UV, and down to radio waves for over a year. About 70 plus observatories followed this event all over the world. Okay, and this gave you the first measurements of Hubble's constants from gravitational observatory. Of course, this is nothing in precision compared to what Planck has achieved in the cyan band, but this is the first step. It's soon going to improve a lot. It also gave a cosmic answer to the quest for gold. I mean, there was always this puzzle that all heavy elements were believed to be cooked in the furnaces of stars in their last stages when they turn into a supernova. And but it was known that the supernova, the processes in the supernova explosion cannot produce enough gold, platinum, and these lanthanide series elements for to explain the abundances that we find in the solar system or on Earth. So it was postulated that these must be neutron star mergers that give rise to it, and this one event verified that, because we saw signals of this kind of nucleosynthesis happening in the optical. So in the first run, we had seen these many black hole mergers and one neutron star mergers, about 11 published from the first two observation run, and we had 50 candidates in the third run. I should remove the word ongoing. The third run stopped in April. I'm sorry, this should have been updated. And some of the events in the third run have also been announced. You keep hearing about them now. But if I were to now describe them, they are all unique in their own senses. They have all found something new. And of course, the compendium of all the events is a paper that will be out probably very soon. But let me digress from that, and or rather move towards the main topic of LIGO-India. So I should say that LIGO-India has a very vibrant science community around it, which engages in all the research topics that I've listed here. And people worry about the neutron star equation of state, because neutron star mergers can actually determine for you the equation of state of nuclear matter at high intensities. Okay, and various tests of generativity are being done, and generativity has passed them till now with flying colors, and many other things to do with detectors. So let me get to the detection of gravitational waves. What's involved? Why did it take a century and 40 years of actual dedicated work to measure gravitational waves? That's because the signal is very small. So the signal is a strain in space, so that two objects are displaced by a small, two objects at a length separated by length L are displaced by delta L, and delta L over L for the sources we're looking at is 10 to the minus 21. So if we are looking at objects placed 4 kilometers away, that translates to measuring displacements of the order of 10 to a minus 18 meters, so attometers. Okay, this is few orders of magnitude smaller than the known diameter of the hydrogen nucleus, and of course many orders of magnitude, a billion times smaller than the size of a hydrogen atom. Okay, and so in this quest we have breached kind of a threshold in our ability to measure displacements, and that's called metrology. To measure is metrology, and the best metrology or measurements of various kinds of estimations of sizes as of the nuclear sizes, and that is 10 to the minus 15, a femtometer. And to detect gravitational waves, we have to find a way apparatus that can measure displacements of the atometer scale. And for doing that, of course, three gentlemen got the Nobel Prize in 2017. Rainer Weiss dreamt of the apparatus and actually pursued the construction of it and design. Kip Thorne was the theorist who essentially saw the potential of what gravitational waves would bring, and how they could be, how the sources are and what kind of sources. And so these are leading figures in the field. And Barry Parish was a very important person. And in the context of mega sciences, I wanted to spend a few minutes. When you have such huge efforts which involve 1,000 people, one, of course, you have to be great scientists, and Barry Barish himself is a very well-known experimental physicist, particle physicist, but he is also an extremely good scientific manager. And he brought this collaboration to fruition and, sort of brought the LIGO-India discovery. And in that discovery, for example, because of our participation in our efforts to build LIGO-India by then, we were already partners in the discovery with 37 authors from 9 Indian institutes. A lot of the science work was also done in the Indian institutions. And at this time, we have 100 plus researchers in the LIGO scientific collaboration. So how do we measure such tiny displacements? So what a gravitational wave does to a lattice of points is this following. You can see that there's a lattice of points here. As a gravitational wave passes, it sort of moves the particle around. And if I were to monitor the position of a ring of particles in this field, the ring would be doing this. It would be going from a circle to an ellipse, and then an ellipse in a perpendicular direction. The major and minor axis exchanging each other. And this is the dance they're doing. But remember, the dance is where the red dots actually here very visibly moving. They are moving for gravitational waves at the level of 10 to the minus 18 meters. And how do we detect such motion? And the best metrology tool we have in physics is an interferometer. And many of you may be familiar with the Michelson interferometer, where laser light is sent down and to a beam splitter, which splits it along two paths. And they bounce off a mirror, come back and interfere. And you can set it such that when the two lengths of the mirrors are exactly the same length apart, there's destructive interference and there's no light at this output port. Okay. So there is a dark port. It's not exactly dark when you operate, but let me, for simplicity, assume that. And when there's a gravitational wave, you see what this ellipse is doing. It's stretching in one direction. So this circle here becomes an ellipse. So the length increases along one arm and decreases along the other arm. Okay. And then what was destructive interference allows some light to leak through. Okay. Now again, here the arrow makes it looks as if, it's a completely constructive interference. That is not true. The motion is at the level of 10 to the minus 13 radians, the change in phase. Okay. But we are accurate enough to measure that tiny change. So for doing this, you need to place this interferometer on huge scale. It's not a tabletop Michelson interferometer that physics students may have seen in their labs. It's something that is enormous. It's 4 kilometers long. And when I started looking for a site for this in India, it took me some time to even come to terms with what 4 kilometers is. And this is 4 kilometers on this side, 4 kilometers on the right and other angle. And this is the Hanford and Washington, USA detectors. There, the laser light cannot run through free air because the air has a lot of molecules which will introduce scattering noise that will completely swamp your signal. So you have to create a vacuum tunnel or a vacuum tube for the 4 kilometers on each side. So 8 kilometers of long vacuum tubes, and these are 1.2 meters in diameter. So you can see someone standing inside one of the tubes and installing baffles there. And this tube is protected by a concrete shell, and this is the concrete shell in Hanford. And you can just see the scale. I mean, everything in this is the main central thing where various optics are housed. And you can see that there are people standing here, and the size of the vacuum chambers which houses the optics of this. So the optics looks very, very, high end. These mirrors are 40 kilograms. The primary mirrors are 40 kilograms in weight and 34 centimeters in diameter. So they, you can't lift them with your hands. So they're, special jacks which do that. And then they are placed inside on a suspension system. And when you do all that work, you are dressed up like a surgeon, okay, because you have to have ultra high cleanliness, because even a speck of dust settling onto these mirrors will spoil your experiment. These mirrors on these scales have less than a tenth of a nanometer kind of figure accuracy. The roughness figure is that, and very low absorption. Okay, these are numbers. So just put it bluntly, of course, astronomers pride themselves on having the best mirrors, uh, because they are the ones who use them for telescopes. And the surface specs is 100 times better than the best telescope optics that you have. And this has really spurred, the LIGO-India project has spurred a lot of activity in our own labs to try and achieve such high quality optical, elements in our own laboratories and industries. Then there is a very intricate system of suspensions which provides 12 orders of magnitude isolation from the motion of the ground. Now, even in the quietest place on Earth, if you measure the ground motion with a seismometer, you will find that the ground is vibrating at micron level. Okay, a micron is at least 10 to the 12 times larger than 10 to the 18 that we are trying to measure, right? So we have to find a way to isolate that noise from the mirrors. And the mirrors are also very pure objects. These are very unique objects. They are cast in one lab in the world. They are polished in another lab in another country, and coated in an industry in a third country. So these are unique capabilities and very unique objects that are created. And these mirrors, believe it or not, 40 kilograms hangs by glass fibers, which are, zero point 0.4 millimeters thick. Okay. And they are welded to the, mirrors, and they are basically, hanging by glass wires. Sounds very crazy, but actually it works. And of course, the fibers have to be extremely pure glass, and otherwise any crack would propagate, and your fiber would break. And so this is an amazing kind of technology that is involved in doing that, right? So when we set up our things, we'll have to hang our mirrors with these kind of glass fibers, and make sure that we are able to produce such glass fibers, and also the smaller optics of that quality. And then there's a laser, and the laser is 180 watts, but that's not, the wattage is not so important. Of course, you've heard of terawatt lasers nowadays. So tens of terawatts is also talked about. So that's not the main point. The point is those are pulse lasers, and this is a continuous laser. And it's a continuous laser at that wattage, and it has an extremely narrow line width. Now, what do I mean by that? Textbook definition of laser is that it's a monochromatic source of light. Monochromatic means there's only one single frequency. Of course, no laser or no object is ever monochromatic. Okay, no light is ever monochromatic. There is always a spread of frequencies around that central frequency. Here, the spread is 1 part in billion. Okay, and that's very, 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 very difficult to achieve. And these are very intricately set up laser systems which clean the laser noise to a level where you don't have fluctuations in intensity at parts per billion, and the frequency stability is at millihertz. This is unique, and again, this is something that is under development at various labs. Of course, we will get the first version together with the you know objects that will, I mean, the TA components that will be supplied with it from LIGO lab. And then there is also
Uh,
quantum technology
Thar,
involved. Sorry.
Tarun, can we ask one question at this time?
Yeah, sure.
Okay. Hariom, can you ask?
Yeah, sir. Actually, I am having two questions. One question is this: you have shown the tunnel. So I think roughly the diameter of that tunnel in which this laser light will go is roughly 6 or 7 feet because a person was inside that. Is this correct?
No, it's 1.2 meters. So it's not really a person's height. And
Okay.
this, yeah. So this is 1.2 meters is like a typical person will be 1.7 meters. Okay,
Okay.
so you
So
have to fold yourself half a meter. So this
okay.
maybe,
Then sir, this why this much? Why you required this much diameter? Because this laser
that's
is I think pinpointed.
no, it's not pinpointed. The laser waist or the narrowest part of the laser
Hmm.
is 12 centimeters. Okay, so it's
Okay.
a 12 centimeter beam spot. Okay.
Okay. Sir, my second question is, you put this mirror side this for the to isolate it from the seismic noise, right?
Yes.
At that figure, you are saying that we want to isolate it from this background, but the problem is
Mhm.
this when this black hole will merge, they will this whole space time will like there will be like they will move like there will be a ripple, right? So
Mhm.
so whole earth according what I am thinking is this whole earth or this whole system will move, so you cannot isolate it.
No. So yes, we cannot isolate gravitational motion of the thing, but you should realize that the amount that a solid rod would move
Hmm.
versus two freely hanging mirrors would move is different. Okay, to the same gravitational wave strain, right? So, for example, if I try to apply a strain on
Hmm.
something which is soft, that soft thing deforms much more than a hard thing, right? So freely suspended mirrors move.
Hmm.
Of course, the tube and everything also probably entire Earth actually shakes a bit, but
Hmm.
those are very tiny because these are solid objects.
Uh, but I don't know where I'm doing the mistake in understanding because how we will distinguish it because the this whole space time is like moving, like how the seismic wave is different than this.
No, the space is contracting in different ways in different directions. It's not so one arm is shrinking. The relative spacing of the two mirrors along one arm is shrinking. The other arm it's extending. When the other arm is shrinking, the first arm is extended. Okay, so that is where the signal is built up.
Okay. Okay, sir. Thank you.
Okay. Yeah.
Okay. Great.
Okay.
So I wanted to point out briefly that now the generation of advanced LIGO detector, of course, even from the day it was started in 2015 in its advanced state, has been continuously upgraded. So at this point, for example, the detectors are shut down for an upgrade. And the expectations is that we will be making quantum measurements to further improve the signal to noise via using squeezed light. So we will play around with the state of light, quantum state of the light, and then we can do that cleverly to beat, Heisenberg uncertainty to our advantage. And this is something that is broadly a field of quantum measurements. And there's a lot of potential technology spin-offs in quantum computing and quantum key distribution. And there are a lot of people, I mean, in India, we are heavily into quantum technology nowadays, and LIGO India actually complements that with a physics apparatus that uses quantum measurements on macroscopic scale. So what is amazing, I would like to, I always find it very amazing, and particularly for students, I know that many students, young students want to work on quantum physics, and they're very excited. And LIGO presents for you a 40-kilogram object that is behaving quantum mechanically for us, because when you're trying to measure displacements of the order of 10 to the minus 18, you are pretty much competing with the quantum fuzziness of a 40-kilogram mirror. Okay, and we actually try to use it to our advantage. Okay, so now why LIGO India? So I talked about what a gravitational wave observatory of this generation sounds like. Setting up a detector in India is, very, very strongly motivated by the science it will enable. And what kind of science? That's because if you looked at the first event, although we knew that a black hole had merged, we didn't know which galaxy. I told you in a galaxy far, far away, but we did not know even where in the sky was this galaxy located. And that uncertainty is given by this big banana shaped uncertainty region. Okay. If at that time LIGO India had been operational and at the same sensitivity, then we would have actually located the source to this tiny ellipse here. Okay. So we would have gone down from, area in the sky, 100 times smaller, from 620 square degrees to 5 square degrees, right? So it will make a big difference when it comes up. And it is on its way. So here is picture 3D rendition from actual architectural drawings. So there's actually a full video which can do a walkthrough of the facility, and this is how LIGO India will look. And actually the terrain data is also authentic. It is the actual terrain data there. Okay, and this is a project which was approved by the Union Cabinet in 2016, February 17th. And the site is now acquired as of last year. And we are sort of in construction phase, although it's not formally inaugurated, but it's very much happening. So what is the LIGO India concept? It's a Indo-US collaboration with National Science Foundation on one side and the Department of Atomic Energy and Department of Science and Technology on the other, on the Indian side. And the Indian commitment is to the construction and operation of the entire detector. So it is our detector, right? We will work together with all the detectors in the world at that time to do science, because that's how gravitational wave science has to be done. You can't do it with one detector effectively enough. So this will involve, the entire infrastructure of 8 kilometers of ultra high vacuum, so 10 million liters of vacuum with the controls of the detectors as well as the team that will build and operate the observatory. US commitment is the hardware that went into advanced LIGO in 2013. Okay, so the key hardware that went in there will be there, but all the upgrades to that and all this squeezing that I talked about is stuff that we will have to do on our own. Okay, any upgrades till then. But we have very close technological collaboration, not only with LIGO laboratories, of course they are partners, but also with many other gravitational wave groups. So gravitational waves is a community is one community where the entire global community is one single team. Okay, and so if we do LIGO India, it would allow for a full exploitation of gravitational wave observations as a part of astronomy. We will not only know that gravitational waves object events have happened, we will know which part of the sky, maybe identify the galaxy where it happened, and possibly even the part of the galaxy where it happened, so that we can infer what kind of astrophysical environments these sources are located in. And they are puzzles of that kind. For example, these large mass black holes, we don't know whether they are only formed in globular clusters or they can be formed outside globular clusters. And then, of course, there's a high-end technology frontier and that would be transformational for the Indian capabilities. And then there's a strategic geographical advantage because India provides a 12,000 kilometer baseline, which allows this triangulation and the small error bars in your location of the sources. Okay, but one thing that the reason I talk always to never miss a chance to talk to young students is the demographic advantage of India. We are a youth dominated country, unlike many others. And if you want to emerge as leaders in a field and grow a huge technical manpower in the technical scientific manpower in a field, India is probably the richest place to do it because it has the manpower, it has extremely good undergraduate training systems, and we just have to take that up and build upon it, producing providing research opportunity for undergraduates and postgraduate students in science and technology. So the cabinet, when it gave its approval, it sort of saw that it would bring unprecedented opportunities for scientists and engineers. I started with a very big support, and its support has remained. So this is late Dr. Shekhar Basu, who was the former chairman of DAE. Very tragically, he passed away just a couple of weeks ago due to COVID in Calcutta after it, of course, post-retirement. It's Dr. Shekhar Basu who is signing this, and I would like to dedicate my talk to him in his memory. And he is exchanging the signed folders with the director of the National Science Foundation. And the person you see in the middle is someone I'm sure no one will fail to recognize. Our PM took the trouble to be there in person for this signing. So that was the level of top level support that this project has been enjoying. So this was done in 2016, very soon after the approval. And then after that, he has been meeting with the teams at various intervals. Again, here's Dr. Shekhar Basu. And even till recently, there are tweets. I mean, this is already a year old, but there are constantly tweets. And in the recent Vaibhav Summit, for example, inauguration, the PM again mentioned LIGO India. And so why is it so attractive to everyone? That's because it's not just astronomy instrument. It will, of course, do astronomy in these green boxes from X-ray to neutrinos. So, tie up with INOs. And then it will also do fundamental science, the gravitation theory, the theoretical physics initiatives of high energies. But the main point I would like to mention is the technology. This touches the frontiers of technology of 6 kinds that are listed here and probably much more. Sensors, controls, optical, vacuum. And these are, a level which is not at this point well developed in our country. Okay, and I think this will be transformational. Okay, and which will allow these precision measurements to be done with an apparatus in India. Of course, it has a lot of computing challenges also, and that's another emphasis that India is placing. And I told you about quantum technology. I didn't put it. Quantum metrology is broadly one field of quantum technology. So the challenges are huge. So we have the site. We are beginning to. We will be first laying out the civil construction, and then on that there will be this vacuum tube 8-kilometer long vacuum tube, four on each side, that has to be set up, and it has to be absolutely leak proof, 10 million liters, megaliters of space under high vacuum, nanotor vacuum. Okay, and inside it we have to place a very intricate arrangement of optics for the laser. The Michelson interferometer I showed you was a gross simplification. Even this figure I'm showing you is a gross simplification of what actually goes into the detector. But this is just 2 arms, and then the 2 arms are going out this way. So I haven't shown you the optics on the other side. but this is the main central lab in which all this optics will be housed. Of course, the greatest challenge for this project has been to get the site. I mean, I think that's an existential risk to any mega science project. And that was very, very nicely brought to my notice by Professor Govind Sarup, who again tragically just passed away about a few weeks back, who actually built the GMRT. So he came and told me, Tarun, do you think your vacuum tubes and all this will be a challenge? Your biggest challenge is to get the site. And he told me that in 2011. And I immediately took that as a challenge, and we scoured the country, about 40 site leads, and followed up many of them with seismic observations, and various levels of detail to identify the site that we are at now. And there's a very detailed site selection report which is out there. And this is the site. I, of course, love it. And I love it when it's dry. I love it when it's green after the monsoon. And also, there's a beautiful spring bloom in this dry season, but early April. And this site, a lot of construction is already happening. It's all fenced up. There's excavations happening. This is a picture from the geotechnical survey. There are maybe more pictures I could share with you later. And this is an off-site facility which is almost ready for occupation at RRCAT, where the equipment arriving from US will be first tested and then moved to the site. And so this is the off-site facility where a lot of the training will also happen for the installation of LIGO-India. Okay, so let me stop there because I think I've just been over close to an hour now. So let me say LIGO-India is pretty much on the way. And, we hope to be operational by 2036 for our first joint scientific run. And so that is one window of gravitational waves astronomy that has opened up with these LIGO detectors. For the young guys, there's another one you should really look forward to, is gravitational observatory in space. It's called laser interferometric space antenna. And this is already an approved project of the European Space Agency. And it's to send laser beams between spacecrafts placed million kilometers away. And they will see a whole different wavelength of gravitational waves. This sees gravitational waves with millisecond time periods. This will see a gravitational wave with minutes to hours. Then the pulsar timing array is also becoming very mature. In fact, very recently they are kind of hinting that they are probably very close to the threshold of detection of signals from supermassive black hole coalescence. Okay, and these are at nanohertz. Okay, year to decades time scale. And the most prized thing, which I personally, of course, love, is the gravitational waves from the beginning of the universe. And these are encoded in the cosmic microwave background, an area that I have worked on. And this is something that is expected to open in the next decade again, on this decade now, it's 2020. And so hopefully we will do it in the first half. Otherwise, we'll wait for space-borne experiments to see it. There's one Japanese proposal. There's also, interestingly, a proposal to ISRO that the Indian community has put, which is again in joint collaboration with other space agencies. And that's called ECO from CMB Bharat Consortium. And hopefully these will be the exciting things the young people listening in would follow up on. Thank you very much for your attention.
Yeah, thank you, Tarun. That's a fantastic lecture. I definitely think it would have been great if there are more younger people for whom we are kind of addressing these lectures. And today's is really a textbook type lecture inspiring the younger people. all the way from the exciting physics. This particular slide that you have it on, that really tells what kind of canvas that we have spread out for the next 20 years. Really changing the way we look at astronomy now, become multi-messenger. But what is also you have put in so beautifully and so well to the Indian context is in kind of emphasizing time and again the technology component, the part where there are so huge technologies and spin-offs that are coming from such a great experiment. You listed a half a dozen of them, but I'm sure there are many more.
A lot more, yes.
Many the kind of scales of these measurements. It's just mind-boggling to some way. Talk about the kind of phenomena that happening at such a huge objects, but at the speeds of what we look at particles inside LHCs and so on. It's a great canvas. That's all I can use the word. Every sense of physics, technology, and great opportunity for younger people. Anyway, I mean, there are already quite a few questions waiting for you, but I hope at least this video will be seen by more people over a period of time, and there will be a bigger excitement. And of course, there is a project that's waiting and all that unfolding, and you could see that there's a ground zero work happening in terms of civil construction and all that. Exciting times ahead for the Indian community. Having said that, let me quickly go to questions. There are quite a large number of questions on YouTube, but there are also questions on the Zoom. So let me take just one or two questions from Zoom and then go to YouTube. Okay, Shailesh, you can go ahead. Shailesh, can you ask your question?
Yeah, hello, sir. Am I audible?
Yeah.
Yeah, actually, I have 2, 3 questions. First is, since we don't have a consistent quantum theory of gravity right now, so what other things aid us to say with confidence that the quanta of gravitation is a spin 2 particle?
Okay, so any field, quantum physics is quantization of classical fields. So classically, gravitation field is a shear field, and a shear field is spin 2. So that
Okay.
spin 2 part is not a question. Whether
Okay.
gravitons exist is a question
Yeah.
that will not be answered by gravitational waves because these are classical signals.
Okay.
Okay, we use quantum technology of light to measure them, but we are not measuring quantum gravity.
Okay.
Having said that, the early universe signal that I was talking about, which will be seen in the cosmomicrowave background, is a truly quantum gravity signal. Not full quantum gravity, but it's a regime of quantum gravity where it's quantum fields on curved space-time. And the predictions are made using those theories. So if we see them, it is a verification of those theories.
Okay. Sir, my second question is like, uh, while the black holes or neutron stars are merging, they are still emitting the gravitational waves, right? So
Yes.
before they have like actually merged and given us the chirp, we can still verify that we have detected gravitational waves.
No, so the chirp is when the signal becomes at the frequency band which is accessible to LIGO. But the same system, when it is far apart, would emit gravitational waves at millihertz before it emits gravitational waves at hertz and hundreds of hertz. So that will be detected by LISA. So there would be a very interesting situation where we will see sources in LISA, and then based on following the sources for a few months, we will stop seeing it in LISA, and we will predict what time we will see it in LIGO, because the same source will actually again show up in the LIGO bands. Okay, so these would be very exciting times where LISA, LIGO, all these things will work together.
Okay. So, and my last question is like in LHC, the the beams are adjusted because the tunnels are somehow shifted because from the gravity of moon. So are the similar adjustments made for LIGO as well, because it is also a huge
Yes.
setup?
Yes, yes, it's same adjustments are made.
Okay. Okay. Thank you, sir. Thank you very
Okay.
much.
There are two very senior guys waiting on the Zoom, but I would like to go to YouTube because there are some younger people waiting there. I'll come back very quickly. Let me go. Okay, going from reverse direction in a way. Aditya Krishna, what is the scope for mechanical engineers in this mega science project?
Okay, I am a mechanical engineer.
That's right.
But unfortunately, I'm not using my tools of my trade. But I must tell you that the fact that I had an engineering background did help me with this project in a big way. Okay, minimally I can read engineering drawings without any trouble. Okay, so but also but for mechanical engineers, it's immense. The entire seismic isolation is a
Yes.
mechanical engineer's dream. Okay, it's a whole system of leaf springs and pendula and the response functions of that, and then there's a active isolation table that has feedback loops. In fact, I forgot to mention, but when you talk about the control systems, LIGO has about 100,000 control channels output. Okay, and so it's a control systems monster, but also I mean, I always see that people who would learn to work on such machines would be good for any kind of control system things, be it robotic control or missile control or whatever, spacecraft control.
Yeah, very nice one. Niharika Jain, uh, was there space and time before the Big Bang that we may get gravitational wave from CMBR?
In certain scenarios, yes, but not the most popular ones. Okay, so let me say that in the most popular versions, there is a Big Bang, but soon after that, there's a period of very rapid expansion called inflation, and the gravitational waves emanate there. But having said that, there are people who believe that there was a earlier phase of the universe which collapsed and then re-expanded, and but then in those cases, actually, their expectation is that we won't see any gravitational waves in the cosmic microwave background. So this will be a distinctive feature of the inflationary scenario.
Another question from Abhinav Chaudhary. Do the noises in the gravitational waves may indicate towards the presence of the particles which are gravitons?
No, not because in the first wave that I showed you, there were about 10 to the power of 60 gravitons. So when you have such large numbers, the system is classical. Okay, so if you wanted to think of gravitons, it's a it's a conglomerate of 10 to the 60 gravitons.
There's an interesting question. Is there any joint search going on for gravitational waves coincident with high energy neutrinos, since
Oh yes,
are great cosmic messengers?
yes, yes. I forgot to mention that, but thanks for asking this excellent question. In fact, LIGO collaboration has papers together with neutrino observatories like IceCube and Antares, and there are papers where we are using both neutrino, I mean, looking for neutrinos from the gravitational wave events.
So now let me take some real experts questions. Dr. Pitambar Singh, wonderful talk. My question is, what will be fallout if Indian does not meet the timeline and components from others are ready. Okay, so this is
No, fallout in the sense that that's not part of the plan. We have a very well-defined schedule, and so there could be delays, but I mean, at this point, we are not thinking that there would be delays. Uh, if I don't know what you meant by components. If the components from US don't arrive,
yeah, that's what it seems.
they are already in kept aside for LIGO India, so there's no reason for them not to arrive. I mean, it's only waiting for us to go and pick them up when our
The ground.
building at the site. There's a building to store them in.
Okay. So now comes to Professor Vivek Datar.
Can you hear me?
Yes.
Hello?
Yes, we can hear you.
Okay. A couple of questions. Yeah, a couple of questions. One is, what limits the accuracy of the pointing accuracy? Is it the systematics in the modeling, and or is it more in the timing? Because of course it's a relatively slow signal. The order of you have to determine the shape of that, and some fuzzing around of that vis-a-vis measurement, but also with regard to modeling. So is that the main source of error in giving you pointing accuracy?
Yeah, so it's largely pointing is due to the time differences of arrival at the three detectors. It's an identical waveform. So there are many points to compare against. So there's a periodic waveform, and you can clearly have many points where you can use the measure the time difference from. So time difference measurement is quite okay, but you need multiple of them, and you also need a large baseline, so that you have a large enough time difference so that your triangulation is more.
No. My question was the following: that given that you will have India LIGO, is there a possibility that you might improve on the 20 moons kind of solid angle, possibly with better timing or better modeling?
Better modeling, of course, if we can, we might, because we will also have polarization information, and that actually gives you indication of the inclination of the plane of the orbit of the coalescence system relative to the sky, normal to the sky. Okay, so because that is degenerate with distances, so that will allow us to even locate it in radial distance, how far the source was. And that is an important aspect. We'll also have more capability with multiple detectors. You infer the polarization better and better. And in terms of timing accuracy, it's not so much of the sampling rate, as you noted that the signal is not a very high frequency signal, right? So it's not a spike or something like that. So that thing is not. It's a bit different from the considerations in other areas.
Okay. The second question is thanks. The second question is, what are the possible improvements in sensitivity of the present advanced LIGO system that you envisage in the next few years?
Okay.
Apart from the squeeze light. Okay, the squeeze light is one definite thing that
squeeze light is
happen.
one, but the coating noise. So the current limitation, even when we get squeezing, we can't go very far, because what will start dominating the noise budget is the fact that the surface of the mirror has a coating, okay, which is amorphous, okay, and it is some titanium pentoxide or something like that, okay, and those kind of things have a particular level of mechanical response, which is the Q factor of the coating is much poorer than the bulk mirror, okay, and that is what limits us. So there are people, there's an entire effort to look for a different coating. And in fact, one of the areas of research in India, where a lot of people from a very different field of um, can collaborate and with the LIGO-India project.
Okay, thank you very much.
Yeah.
Thanks.
Okay, sorry, Deepak, for making you wait. Now it is your turn. Deepak. Deepak Chakrabarti.
Hello?
Yeah, we can hear you. Please.
Okay, my question is actually very, very trivial, and I am sure there is a trivial answer to that, but let me still ask it. If you want to detect by interferometry a change in the dimension of 10 raised to minus 18 meters, is it or is it not that the smoothness of the mirror or the fluctuation and the modulation of the mirror should be better than 10 raised to minus 18 meter?
No, no. So of course it can't be, because
Yeah.
that's much smaller than the. So this is, of course, that's why anyone who should hear this should think that this is a crazy dream. But what's happening here is that there are two things. One, let me explain the simpler part of it, which is that you are averaging over Avogadro number of molecules, because as I told you, the beam spot is 12 centimeters.
Uh-huh.
Okay, so the fluctuations on the surface average out. Okay, now you can talk about the mechanical vibrations of the mirror. I told you that
Yeah.
the Q factor of the mirror is 10 to the power 8, and the resonant frequency of the bulb, mirror bulb, is kept far away from our measure, interest of the band of interest from 10 to a couple of thousand hertz. Okay,
Uh-huh.
so 10 hertz to kilohertz, this is far, far above that. So, and it's, since the Q factor is very small, all the mechanical vibrations are actually peaked there, far away from our frequency ranges. So what the way to think about it is, the surface is vibrating at frequencies much, much higher and get averaged out on the time scales that you're looking at. The gravity wave signal is at 100 hertz. So the modulations are at 100 hertz that you want to measure. But there are, say, 10 kilohertz noise vibrating of the vibrating object, but those are, averaged out.
Okay.
Just,
Okay.
yeah,
Hello?
please go ahead, Deepak. Please go ahead. Please go ahead.
No. I'm saying that I got the technical answer, but it's difficult to for me difficult to get it in the system that change of 10 raised to minus 18 meter is really being seen, and it is amazing. That's all.
Yeah, it's no wonder. No, I mean, there's no wonder that it's amazing.
Yeah.
But you can work these out, and actually you can show. See, essentially, when I said it's averaging out over the Avogadro number, you are averaging out the vibrations relevant to your frequency band, which is leaking from a system with Q factor of 10 to the power 8. Centered on a frequency far, far away from your band of interest.
Okay.
Right.
The other trivial question was hello.
Hello. Yes.
The other trivial question is that just by detecting the gravitational waves, we cannot say whether it is neutron star merger or the black hole merger, right? Just from the waves.
We can actually, because the masses of neutron stars are 1.5 solar masses and all, and black holes typically astrophysically are formed above 7, 8 solar masses, 5 to 7, and there is actually something called a mass gap. And recently in the gravitational wave news, you must have heard of a system that was measured, which seems to have a mass which is in the mass gap. So where we astrophysically don't expect objects, we end state of stars either gives you neutron stars, which are 1.5 to 2.5 solar masses, and then black holes, which are more than 5, 7, 10, depending on who you talk to. So there is a gap.
There's a band gap kind of thing. There's
a band gap.
Okay.
But there seems to be a system sitting right in the middle of that. So if you see many of such things, then that will be a puzzle, because we don't know how to generate them.
Okay. Thank you very much.
Recently we have also seen a 140 solar mass coalescence to 140 solar mass, right? So, which is kind of difficult to astrophysically get your hands around. I mean, basically the progenitor masses were too large to be explained by normal astrophysics.
Yeah.
I mean, it can be explained, but no, I mean, the general idea in the field was that such things don't exist.
Okay, thank you.
Okay, thank you.
Okay.
We have
Satya,
two more. Yeah.
Can I ask a question? Piyush here.
Yes. Go ahead. After that, we have a couple of more questions from students. Yeah, please.
Yeah, again, this is a very, very naive question probably. I wanted to know what exactly is ultimately measured. Do you actually see an interference pattern, or is just you initially keep it in null mode and then you see lights, or do you see?
Yeah.
And what is actually hidden in the interference pattern itself? Do you use that?
No, there's no, we don't see the
No.
pattern at all. So we are at the dark spot. We are
Right.
not at the dark spot. I mean, to you, I can explain. So there's a curve, and the dark spot is at the bottom of the curve, and that's not a good place to be in, because it's a quadratic function there. So you move off that to a linear part of the curve, so slightly off from the dark spot, where there's a linear response function. Okay, and there, what you're measuring is 10 to a minus 13 radians of phase shift.
Sorry, what? I didn't follow
You're
that.
measuring a phase shift of 10 to the minus 13. Delta phi that you're measuring is 10 to a minus 13.
Okay.
Okay.
Is that all the signal that you use for extracting all the, or
Yes.
are there some additional?
No, that's the main signal. Of course, then there are other things that you're corrected for, but this is the primary thing that we are looking for: change in the light at the photodiode around that, slightly off from the dark spot in a linear regime at the level of 10 to a minus 13 radians.
And you mentioned that, of course, there is a spread. It's not exactly monochromatic, of course, but so
Yes.
why isn't there at all any, digitized version of some kind of interference patterns?
Digitized? Sorry?
Some kind of alternating bands of darks and light spots.
Yeah, but you're not looking at pattern at all. You're looking so closely in the pattern that you are at one spot in that, right? So you are not even moving from, at any time within the, kind of the wavelength of the light thing, or the period of the interference pattern.
Okay.
Right? So you're well within the same spot
Okay.
of the interference curve.
Thanks.
Yeah, there are three more questions. I hope we can quickly finish that. Hariom, can you ask quickly?
Yeah, sir. We can measure. Suppose there is a black hole, this merging event. So can we measure the this direction of that event? Because this distance we can measure, I think, by this amplitude. So if the more amplitude, it means the event is very closer, and like that. So can you measure the direction?
Yeah, so direction it requires the multiple detectors, and as I said, triangulation improves with detectors spaced as far apart on Earth as possible. So LIGO-India provides a distance which is 97% of the largest distance you can have, diameter of the Earth. Okay, so that's a very large baseline. The first question, the first part, you said that distance is easy to measure. That's not quite true, because the amplitude is true, that the amplitude is a measure of the distance, but the point is you don't know how the binary is tilted with respect to you, and the amplitude does depend on that. Okay, and so that's a degeneracy, and hence the distances are not accurate. But LIGO-India will able because we will have polarization information, we will be able to infer more about the orientation of the binary with respect to us, and hence we will be able to give distances to the sources much more accurately.
So with this other observatories, with the other LIGOs, you can measure the direction. Do you want to do this?
No, with two of them, it's very difficult. I showed you how little you know.
Many other, like in other countries also
Many,
there are.
Yeah, Japan also.
yeah,
Right? Japan also.
Japan and all that. So, but they have to be comparable sensitivity to be useful.
Okay.
Okay, so all observatories of comparable sensitivity can be used effectively.
Sir, I'm having one more question, very small question. So what is the frequency of your this events, this black hole merging? Is this event very rare, or this neutron stars also you can measure?
No,
So
so based on our current guesses from whatever we measured, if we have full advanced LIGO sensitivity, we will, or suppose we had detectors which could measure all black holes happening, we'll be measuring one coalescence every few minutes. Okay, so even with best LIGO sensitivity, we are expecting in few years, maybe five years from now, to have event every 15 minutes.
oh.
Oh, that is great. Nowhere near your neutrino events, huh? Hariom. It's fun.
Yes, sir.
Okay. So one more question from Shailesh. You want to ask yourself, Shailesh, or you should read it for you? Okay, let me read. Can I follow up on my earlier question? On a slide, some signals were recorded before the chirp as well. In such an event, how much time before the merger are the waves measurable, and can it be predicted before the chirp that after a certain interval a merger event is coming? So something
Yes,
like that.
that's a very nice question. In fact, that is the target. So it depends on what is the size. So for black holes, typically in LIGO band, they merge at about few hundred hertz. Okay, so the time you have is about in the first one you had only 0.2 seconds. In lighter black holes, you probably have a few seconds. But for example, the neutron star signal lasted for around 30 seconds. Okay.
Oh.
And sorry, there's a Dr. Suresh who's trying to talk.
Hi. I think this is Suresh Kumar. I think Suresh Kumar will just hold on. We will take.
Okay. Okay.
Yeah.
So as I said, so for neutron stars, for example, we have quite a bit of time when we start seeing that the signal is coming till the time it merges. So for neutron stars is also interesting because we can alert observatories. We can tell the gamma ray telescopes to watch out for a event. Okay, and this is interesting because then we need to send out early alerts, and our target is to try and do it 90 seconds before the merger. Okay, so neutron stars, I'm sorry, I said 30 seconds, but they last more than 30 seconds, few minutes actually. Okay, so you can send out alerts, early alerts. But at this point, that is still a to-do. I mean, we don't have very early alert system that's reliable and can point to the part of the sky. In that case, a project like Daksha, which is being proposed by Varun Bhalerao, is very interesting because it will pick up a signal at whatever time of the day, whenever. So from most directions. So it's very interesting space mission plan proposed by Varun Bhalerao from IIT Bombay to ISRO, and I hope that is there. It's a all-time gamma ray monitor, gamma ray X-ray monitor for gravity wave follow. There'll be 2 satellites orbiting Earth.
Actually, before we go to Dr. Suresh Kumar, one question from Dr. Bitam Singh. I think that also reminded me. You didn't quite say where the exact location of the Indian.
Okay. It's in Ondha district in Ondha Taluka in Hingoli district of Maharashtra. Okay. In fact, INO experience kind of informed our collaboration not to talk over the site for a long time till we had it all under wraps. And so, yes, so it's in Onda Taluka and it's very near a well-known pilgrimage site called Onda Nagnath. It's one of the 12 Jyotirlingas or something in Maharashtra. And so it's visited by many pilgrims every year.
Also close to Nanded, right? That is also.
Yeah, the Nanded is the closest well-known city.
Yeah, that's also high.
That's about 70 kilometers, 60 kilometers from the site, 60 to 70 kilometers.
Okay. So, Dr. Suresh Kumar, you want to ask? Suresh Kumar, can you ask a question?
Yeah. Thank you, Satyanarayana.
Yeah. Sir.
Let me first congratulate and compliment Tarun for beautiful talk. Actually, I am not an expert in this gravitational wave interferometer or things related. So my question may be very simple. Or I thought first that there is some parameter which will validate this experiment, LIGO experiment and other things. Is it true? And if it is true, then before validating that parameter, how much we can talk about distance of the event taking place and other things?
Sorry, what parameter? I'm not sure what you. I didn't understand your question. Right.
About the gravitational wave.
Yes.
I don't know, gravitational graviton mass, or there are. I had the impression they will validate or measure
No.
the.
So it's not like a high energy physics experiment where we are measuring the mass of a new particle. There are no gravitons. It's a classical signal. It's like your FM radio picking up electromagnetic signals. Okay, so it is exactly like that.
So all the parameters required are well known.
Yeah, well known. Yeah. So it's essentially a classical wave. Yeah.
I think he's probably referring to some kind of calibration of this. How do you actually calibrate the entire? I think if I have got it.
Yeah, possibly, but I don't really know whether, I mean, so calibration is done. So we know what amount of light in the photodiode corresponds to what strain amplitude, if that's what your question was. Because we can artificially move the mirrors and create these patterns. We
So
can,
probably since there is no gravitational wave before, I think so. Probably if you referring to, do you artificially create? You can create signals. What
yes, we can create signals.
We can. So that's what probably.
Yeah, so that's what I'm saying. So every mirror has control systems which allow the mirrors to be moved. So in fact, there was a period before the first detections, in fact, in the initial LIGO era, where false injections were done to make sure that the data analysis team can pick them up. And one such event actually went too far enough to be drafted as a physical review letters paper, because it was a clear gravitational wave signal till an envelope was opened by the LIGO director, which confirmed that it was actually an injected signal. So these were blind injections done. So no one knew, only 2 people or 3 people would know that injection was done, and a sealed envelope would be given to the director of LIGO. So just before you're ready with the paper, everything had been done. So I'm not sure if many of the postdocs jumped off their top of their buildings or not, because they probably spend sleepless nights thinking that they'll be at the beginning of a new era of detection. But
Okay,
this is
Satya,
called, big
trivial
dog
question.
event.
Yeah. Okay. That's good, Kumar. It's fine.
Yeah, another small question.
Yeah. Can we finish,
If
because it is 7:40 now already?
yeah, two mirrors are at 90-degree. How much accuracy is needed for this 90-degree, and why?
Oh, that's not extremely critical, but that's we have measured it to the third decimal point. Okay, but even if it was slightly off, if suppose our site requirements were such that it was some, I mean, you'd have to play around a lot with the optics to accommodate that. But it's in principle possible to have a detector which is not exactly 90-degree.
No, more than
But
90-degree. It is the value. Yes, value is needed, right? Let it.
so value has to be measured to very high accuracy. So we have
How?
done differential GPS measurements that I think gives you at least 3 orders of magnitude in accuracy.
It's a very difficult task.
No, it is standard in for surveys. This was done by people who do surveys.
Okay, thank you.
Thanks, Dr. Kumar. Okay, so since it is already like almost 7:45 now, and the speaker has taken good time in discussions and question answers, and as usual, also thanks to all of you who have asked these questions and brought out some more insights and details beyond the presentation of the speaker. So on behalf of all of you, let me thank Tarun for his wonderful talk, very inspiring, and at the same time, obviously, a lot of information in terms of all the way from physics to instrumentation to engineering. So again, we all wish the LIGO-India team great success, and in terms of reaching the timelines, and I'm sure it is going to become part of this network very soon and bringing out a new physics. Thank you very much, Tarun.
Thank you very much, Satya, and I'm also very grateful to have such leading lights of neutrino physics in the audience.
That's good. It was interesting. Yeah, they brought. Yeah.
Yeah.
Thank you very much,
you.
and good night, all of you.